Bismillah ar-Rahman ar-Rahim. Today we will discuss oxygen measurement. First of all, the importance of oxygen, of course, we can realize that whenever we cannot depend upon, for instance, cyanosis, because cyanosis, as a definition, you must have at least 15 gram per liter or more in the circulation, especially in capillary blood, to denote that there is something wrong to the patient. And of course, we cannot depend upon the tachypnea that occurs during hypoxemia, because of course it's affected by anesthetics. And of course, we may have a local cyanotic effect, not a general. So this is why we ought to use different tools to measure oxygen. First of all, the spectrophotometric measurement of oxygen, which we utilize light, where we shine radiation through a sample. We will show it later on. And then we determine the quantity of radiation absorbed. So we are shining, and then we are determine the absorption. The wavelengths, of course, we must be choosing for such absorption. There are two laws that you must recognize during the spectrophotometric measurement. First of all, the Beer's law. It's correlating the thickness of the media to the concentration. And the second one is Bogart's or Lambert's law, which states that different types of thickness of different materials are absorb light at the same frequency. You see? The spectrophotometric method is based to differentiate between the two types of hemoglobin in the blood. This is why we call it an oximeter. First of all, the test is being applied on hemolyzed blood to detect the absorption of the different types of hemoglobin. We always use two wave. You must memorize 660 nanometer, which is less absorbed by the deoxyhemoglobin. This makes the color of oxyhemoglobin red, and the other frequency, which is 940 nanometer, the absorption is greater than oxyhemoglobin in such wavelengths. The point on the curve we will show you, there are the different curves, two curves with difference regarding the absorption of the two types or the different light wavelengths. We have the red and the infrared. So sometimes there are similar absorption of the two types of hemoglobin. This point is called the isobistic point, which was used in the previous old oximeters. During the in vitro oximeter, we hemolyze the blood in a cuvette. As you can see, we have a pump. I'll show it later on. This type, we have a source of light. This light goes through filters. The filters are designed to give a special wavelengths. You see, it can be on a rotatory device, or it can be given one by one. You see, monochromic wavelengths. And then we have an additional reference line splitted by a mirror. You can see the light after being passed by the hemolyzed blood, where there is hemoglobin and deoxyhemoglobin and oxyhemoglobin, which goes to a detector. The light is split to another one, goes to a reference container containing no hemolyzed blood. So we are comparing the difference between that in this area and that in this area. So this is what we call the spectrophotometric method to measure the oximeter. It of course compares the difference of the absorption of the two types of hemoglobin and calculates the oximeter. This we call it a rotatory disk, you see, or we can use several light emitting diodes. A diode means is a device that gives me a monochromic wavelengths. A correction for carboxyhemoglobin, of course, we know carboxyhemoglobin is due to inhalation of carbon monoxide. Most workers working in factories get a high amount of carbon monoxide. Of course, we have different types of oximeter where they can measure the types of hemoglobin as carboxyhemoglobin and methemoglobinemia. Methemoglobinemia means that the ferrous is turned to ferric. Of course, whenever I measure the saturation in hemolyzed blood, we call it in vitro, and whenever I measure it through the ear or the finger nail, I call it in vivo. The pulse oximeter we emit, of course, in this apparatus, the oximeter we emit red light emitting diode, which is in the range of 660 nanometer, and an infrared rays, which is in the range of 940 nanometer. Shine light through the finger, you see. And there is a photocell that detects the transmitted light. The output of the sensor is processed electronically to give pulse waveform and the arterial oxygen saturation. Sensors also are being used for the ear. You have special sensors for the ear also. Sometimes the sensors of the finger are not correctly or they don't give correct results whenever they are applied on the ear. The diodes are switched on in sequence several hundred times of a second. Why? Because they want to ignore the light outside the system, coming from suppose the veins, from the skin, from the outside atmosphere. So it gives the time for it to process and ignore these signals to give me the proper oxygen saturation. They are equally accurate, but there are some inaccuracy when there is a peripheral constriction, and whenever we are using, of course, the finger sensor for the ear and the pigments, as we know, in the fingers. And these are the things that make fallacies during measurement of the saturation. The oxygenation of the brain is measured utilizing the cytochrome redox that is present in the brain through absorption light in the near infrared. The near infrared is being produced by a laser, semiconductor laser. There is an emitting diode and a reflecting diode. Whenever it hits the brain, it comes back, and through this system we can measure the oxygen saturation of the brain. Of course, oxygen content, you ought to know that it is calculated by multiplying the oxygen saturation in the oxygen times the oxygen concentration of hemoglobin times the oxygen combining power of hemoglobin, plus the oxygen present, of course, in physical solution. This is the amount present in chemical solution. This is plus the amount present in a physical solution. Of course, it's measured by what we call Van Slyke apparatus, or by what we call Lex O2 con. It is a system where the blood is hemolyzed and the oxygen is being released, taken by oxygen-free carrier, and estimating oxygen by the fuel cell. Of course, there are the interrelation of oxygen saturation, oxygen tension can be, or in other words, the saturation of oxygen can be gained from the oxygen saturation curve. Nowadays, of course, putting in mind that we must correct for the effect of hydrogen on the curve, and we know that there are factors affecting the oxygen dissociation curve, shifting to the right or to the left. As we know the 2,3-diphosphogylicerate in the blood, and acidosis and alkalosis, and the temperature affection on the oxygen saturation curve. Whenever I want to know the proper oxygen tension, we cannot depend mostly on oxygen saturation, because sometimes the oxygen saturation, for instance, can be in a range of 90s, yet the oxygen tension in the blood is very low. This is why you ought to measure oxygen better by taking the blood sampling, measuring oxygen tension. Of course, measurement oxygen tension is measured by what we call the oxygen electrode. It's called also Clark electrode, polarigraphic electrode. It is made of two electrodes, a cathode and an anode. We have a cathode. Both are made of silver chloride, and we have a solution potassium chloride, and we must apply a voltage of 0.6 volt. This is very important to create the transfer of oxygen through the cell. What happens really at the anode? There is the reaction between the silver and the potassium chloride, creating electrons. The electrons go through the cell to the cathode. Whenever oxygen is being introduced through the membrane, it unites with the electrons, inducing a current. This current is being measured by the ammeter present in the cell. Of course, the more oxygen available, more electrons will be taken. Okay, analog to what happens in the mitochondria. Of course, I'm sorry, we have a platinum cathode and a silver chloride anode. Of course, this system must be separated by membrane, otherwise the protein will be displaced on the electrodes, and we must check the membrane every now and then for tears, as it may affect the measurement. The system must be kept at 37 degrees, otherwise compensation must be done. We must clean, of course, as we said, membrane from the proteins. The arterial blood sample is being taken anaerobically, of course, and if we don't have enough time, we place it in an ice bag, or otherwise the metabolism of the RBCs will take much oxygen. We have what we call the miniature oxygen electrode. It is a type of electrode that can be used inside the human being, where it can measure, suppose, arterial oxygen tension, whatever, at the CVP and whatever. Of course, the problem as the internal electrodes using the polarigraphic is difficulty in calibration. Of course, as mass spectrometer, polarigraphic oxygen electrode can measure concentration of oxygen in gas mixture. Of course, false results may result in the presence of anesthetics as hallucin, because they are reduced in the presence of 0.6 volt. However, electrodes membrane, especially membranes, are not permeable to hallucin, so they can be used in the operative theater. The fuel cell is also a polarigraphic method, based also on the combination or the reaction of the electrodes with the potassium hydroxide. Here we have the potassium hydroxide, and in the Clark's electrode we have potassium chloride. This reaction, as you can see, yields electrons. The electrons at the cathode is being combined by the oxygen. So the difference are the difference of the electrodes. Of course, we have a gold cathode and a lead anode in the fuel cell. there is no battery, so it is considered as a battery. So this is why it expires after several months. So it needs to be replaced. Of course, we must take off the temperature, and the temperature has been kept constant by a thermistor. This is the difference that between it and the large electrode by the presence of a thermistor. Of course, there is another thermistor present to keep the temperature if there is a failure in the temperature controlling system. Of course, there are type of portable reliable oxygen analyzer where it can be used at the bed side. The problem that nitrous oxide may be introduced to the cell, causing reaction with lead, leading to increase in nitrogen, increasing the pressure, and causing destruction of the cell. This sensor incorporates an audible alarm for oxygen level. Of course, we also have an alarm system, and we have portable oxygen monitors used nowadays, where they use, instead of electrolyte solution, we use a gel. But unfortunately, membrane deteriorates fairly rapidly, must be replaced. The paramagnetic oxygen analyzer, it is a device to measure the oxygen concentration. It is based on most of the gases are what we call diamagnetic. They are repelled from the magnetic field, apart from oxygen and nitrous oxide. The paramagnetic property of oxygen is based on the presence of unpaired electrons in the outer shell of the oxygen molecule. This is why it is paramagnetic. So the cell is made of a box. The box has two glass spheres, as we will show you later on. The glass spheres are filled with nitrogen, and they are supported by a filament, a strong filament. This filament is a balance of tension. So whenever oxygen is being introduced into this cell, the dumbbells will change, reacting to the attraction of the oxygen to the magnetic field, and this rotation will be balanced by the tension of the filament, the strong filament present supporting the dumbbells. Instead of course, this dumbbell are attached to a mirror, and as you can see, there is light. This light is being transmitted to the mirror, and the light will be reflected on a scale as long as the dumbbells are being changed. You see, so this displacement on the scale will show me the concentration of oxygen. On the other hand, or in another way, we can instead of using this method, we can apply electrical coils around these dumbbells, the two dumbbells, and then the reflection of the light will be sensitized by a photocell. This photocell will change this light into electrical current. This electric current will create a current to go to the coils around the dumbbells, creating a current to balance. You see, to balance, so that the system regains this null deflection again. So the amount of current induced by this system can denote the amount of oxygen entering the cell. Of course, the accuracy is around 0.1%, and before use, you must calibrate by two mixture of gas. One of them is free of oxygen, present with the presence of nitrogen. The other one is 100% oxygen. Of course, most this experience gain accuracy from drying the water vapor by silica gel. So whenever you ask why do we apply silica gel in such circumstances, to increase the accuracy by absorption of water. The last slide. We have another third system of measurement of oxygen concentration based on the paramagnetic oxygen analyzer. where we use non-movable parts. What's the meaning of non-movable parts? As you can see from this figure, I'll show it in a bigger one. This is another method to measure the oxygen concentration, where we have what we call pressure transducer, differential pressure transducer system, as we can see the diaphragm. And then we have a magnetic field. This magnetic field is being alternating, and it's on and off. So whenever the system is induced and there is a magnetic field, and then we pass the gas where there is oxygen to measure its concentration. And on the other side, we have a gas free of oxygen on this side. So whenever the oxygen is being introduced in the system, is going to be attracted to the magnetic field, increasing or causing a differential pressure changes. This differential pressure changes will be measured to give me the amount of oxygen present in this mixture. So the point is, we don't have moving parts. As we said before, that moving parts creates what we call some dragging. So it increases the action, the accuracy, you see. So this alternating pressure by the diaphragm will give me a hint about the oxygen partial pressure. Of course, whenever we have water vapor in any gas mixture, it will affect definitely the tension of other gases. So to get a proper amount of tension, we say that the parametric pressure at 37 degree minus the saturated vapor pressure of water at 37 degree is important. First of all, we must subtract both of them, and then after that we can get the real oxygen or carbon dioxide tension in a mixture of gases where water vapor is present there. Of course, continuous in vivo oxygen measurement is a type of Castor polyrographic electrode, where it's been introduced to the human being, especially in seriously ill patient where we want continuous measurement. Of course, the problem, as all internal measuring devices, are a defect in calibration. Of course, the mass spectrometer can be used for continuous measurement of the intravascular by an intravascular catheter. So this is why we ought to, whenever we have a situation, we also it's better to put an indwelling arterial catheter and take sampling to measure the blood gases, or we use what we call the Cutaneous oxygen electrode. This is a system used in especially neonates, where it is a polyrographic, where we have, of course, a cathode and an anode, and we have a heater. You know that, of course, the skin is in need of oxygen, so it takes oxygen from the nearby blood vessels. It may affect the oxygen present in this blood vessel. So, to overcome these fallacies, we cause a vasodilatation of this vessel, so that the oxygen taken to the tissue will be negligible and will not affect the final result, so that the oxygen present in the peripheral capillary will resemble that present in the nearby arterial sample. Of course, it's not invasive. We have a platinum and gold cathode, and of course we ought to heat by heater. Of course, we have a thermistor as long as we have a heater, so that the patient will not be burned. This is why we ought to change the site of the electrode every 3 to 6 hours. And we must put in our mind that the problem of the metabolism of oxygen, of course, takes some oxygen, and this heat makes the oxygen decision care shifted, and edema present in the edema induced by this heat, of course, can affect the results. And whenever there is, of course, decrease in cardiac output, the results will be affected. The response time is slow, 1 meter, and there is, of course, lag behind changes in the arterial blood tension. These are the figures we mentioned before in a bigger site. This is the the measurement of oxygen saturation of the brain, where we have a emitting diode and a receiving diodes. This scattered after hitting the brain will be reflected, measuring the oxygen saturation of the brain. Of course, this is the spectrophotometric method, where we hemolyze the blood in a cuvette and then we pass light through filters on a rotatory drum. This filters yields a special waveform, so it goes to the hemolyzed blood, where there is the two types of hemoglobin, which will estimate later on the saturation. On the other hand, we have a reference tube so that we can compare both of them, because sometimes this light is being changed every now and then. So to assure that we have a proper comparison, we ought to have a reference channel. This is the fuel cell, and this is the thermistor, and we have a lead anode, and there is the plastic membrane and the gold cathode, as you can see. And this is the isobatic point, where the two types of hemoglobin are absorbed live at the same level. And we have, of course, the red and the infrared range of wave forms. Never forget the 690 and the 960 wavelengths, which differ according to the absorption of two types of hemoglobin. And this is the natural paramagnetic oxygen analyzer, and this is the another version where we have creating a current around the coils. And this is the Clark's electrode, where we have a volt of 0.6 volt, and to the cathode and the anode and the special membrane. And this is what we call the pulleys to stretching the membrane, so that no materials will go through it, affecting the electrodes. We must, of course, check this membrane every now and clean it from the dirt and the proteins. And this is the oximeter, and this is the diodes. The diodes, of course, we have two diodes. In the previous old versions, we used to use the isobatic point, but nowadays we use two diodes, one of them for the infrared and one for the red, and they are reflected by passing through the arterial pulsation. There is a program and a processing effect that avoids all what is absorbed around this arterial pulsation, so that we can gain at last the plethysmograph and the oxygen saturation. It is a very long subject, of course, like the vaporizer. So I consider it as in Islam the verse of the cow, al-Baqarah. So I hope that I succeeded. Wassalamu alaikum wa rahmatullah wa barakatuh.